Okay, welcome back. Now the demo that I'm going to do, I'm calling hyperbolic negatively curved geometry. I've done a demo before where I used the surface of the earth, a globe, and it was called positively curved geometry, and it's also called spherical, positively curved geometry. This one is called hyperbolic negatively curved geometry. So I want to show you the features of this kind of geometry, and then this is one of the possible shapes that the universe can have, right? So one of the features of this kind of geometry is that parallel lines will look like this. They will diverge out. We call them diverging parallel lines. They will not stay parallel. On a flat geometry, parallel lines will stay parallel, right? In a negatively curved geometry, they will diverge out. The other things I want to show is that in a flat geometry, the angles of a triangle add up to 180. This is for flat geometry. In a negatively curved geometry, since straight lines tend to diverge out, the straight lines will look like this, right? Like this a little bit. And then when you add the angles of a triangle, they will add to equal less than 180, right? In a positively curved geometry, they will add up to be larger than 180. And I showed that in that other video, in the positively curved geometry video. And then the other thing that's true is that when you draw a circle and when you draw the circumference, the diameter of the circle, so in a flat geometry, the ratio of the circumference to the diameter is going to equal pi, right, in a flat geometry. But in a negatively curved geometry, when you do the circumference divided by the diameter, you should find that the answer gives you larger than pi. Okay. In a positively curved geometry, when we did it, we got an answer less than pi. When we took the ratio of the circumference of a circle to the diameter, we got less than pi. But in a negatively curved geometry, we're going to get a ratio that's larger than pi. Okay. So let's look at here. So I have a shape here, very small, and you can see that it's being carved out. This is 3D printed, right? 3D printed. It's a negatively curved geometry. And it's kind of the same as what's known as the saddle that you put on a horse and you sit on the saddle. That's also a negatively curved geometry, the saddle. So you can call hyperbolic geometry, saddle-shaped geometry, or negatively curved geometry. So if I want to show the first property of straight lines, okay, so after you put the thumbtacks, you notice the thumbtacks, the distance between them is the same. So then I'm going to draw straight line. The way to do that would be to connect them with this string. So just wrap the string around the thumbtack. Okay, so therefore the string will connect the string will form the geodesic. Remember, I've explained that before. It's the shortest line between 2 points on a curved space. A geodesic on a flat geometry, a geodesic will be straight, but on a curved space like this, the geodesic will be curved. Right, so then you just draw the straight line as formed by this string. Just follow that line. Okay, so you can see here, if we shoot a beam of light, right, 2 beams of light straight, if the universe was negatively curved, we would see that the beams of light will go like this. And you see how they're kind of coming closer together here in the center, and then they're starting to move apart here. Okay, so the way we can test this out is that if light actually curved like that, it would distort the shape of the galaxies and the distribution of the galaxies that are farther out. So we've done tests like this, and we've actually found out that the curvature of the universe is more like a flat geometry. There isn't much of a curvature outward, or there's not much of a curvature inward. But you can see here on a negatively curved universe, the parallel lines of light would go like this, and then they would curve outward, right? They would get closer and then curve outward. So this is a pretty good demo, and you see it just by following the curvature of the string. Now the other thing we can do is connect 3 of these thumbtacks and form a triangle. right? So all you do is just put one thumbtack here, okay? And then I can make another triangle here on the other side. Then I can put another thumbtack here on the top. So I'm just connecting one of them here that I already had. Then I'm using one of the upper ones here. Then I'm going to put another one here and then form a triangle by connecting them with a string, right? See the lines connecting them like this is curvy. And then as it's going up, I'm going to go all the way connected to the where the location of the thumbtack was. Okay, so then if I open this up, you can kind of tell it's curved this way, it's curved this way, it's curved this way. So it looks like this. See the one thumbtack is here, then it's going like this up to the top. So since lines naturally tend to do this in a negatively curved space, so they're going like this. And then here the top thumbtack, then you can see here this line is also curved. Okay, and then this line is kind of on the bottom here. And then the line connecting them looks like this. So you can kind of visually already tell that this angle and this angle and this angle, when you add them, they're going to be smaller. The sum of them is going to be smaller than if it was a flat geometry, right? Because this angle is going to be smaller than this angle. This angle is going to be smaller than this, and this angle will be smaller than that. So it's pretty obvious just visually telling that the angles of a triangle on that kind of geometry will add up less than 180. So this kind of geometry was discovered back in the 1800s, okay, as well as the positively curved geometry. The positively curved geometry was discovered by Riemann, and the negatively curved geometry by a person named Lobachevsky, right? So these negatively curved geometry and positively curved geometry, the mathematics describing them was already invented in the 1800s, but they were used by physicists to describe the curvature of space-time in the general theory of relativity by Einstein. So you can see how a mathematical tool can be discovered by pure mathematicians and then utilized by physicists to describe space and the universe, right? The last thing I want to do is more mathematical. I want to actually measure the circumference of a circle and then divide it by its diameter. So I'm going to be using, I'm going to put a pin in the center, okay? So when it's going to be kind of challenging. So press this pin in. So I just have a very short string and then stretch this string as far as possible and then make a circle. Circle, circle, go around. Stay steady. Do not rush this. Stretch out the string as much as possible. Make a circle. See that the circle you get is this kind of this blue line, right? So it's basically the string stretched out as much as possible, right? So then you just kind of follow it, and it goes down, it goes down, and it goes this way, and it goes this way. It's kind of a weird. So the actual circle takes the shape of a saddle. It doesn't look like a circle on a flat geometry. So it's going to be, you see, comes down like this, comes down, goes like this, goes like that, comes down, goes like that, right? So what's going to be the diameter of this circle? Well, the diameter of this circle is, I could put the string next to a ruler, and then that's going to be the radius of the circle, and then I'm just going to double it. So at the left side of the string is starting at the 60 centimeter line, and then the right side is 63. So from 60 to 63, and then if I, from 60 to 63, if I double that, because this is the length of the string, if I double that radius, that's 6 centimeters is the diameter. Okay, so all I have to do is start to tape this string around the circumference. So You can see now I've taped the string around the circle, the saddle looking shaped circle. I started all the way from here, I taped it around, taped it around, taped it around like this, then came back, okay, then followed the circle, and then I'm all the way back. So now I can cut this string, and so now I cut this string, okay, put it to the ruler. Okay, I have the left side of the string at the 40 centimeter line, and the right side of the string is 65. So that's 25 centimeters. 25 centimeters is the circumference of that circle. So if you take the ratio of that, that gives you the value of pi in that universe. So of course it depends on what the diameter of the circle was and what the circumference. If I had made a much smaller circle, the ratio of the circumference to the diameter might have been closer to pi, to 3.14. But since my circle was relatively large in that universe, right, in the curvature of that universe, the ratio of the circumference to the diameter is going to be a lot larger than pi. So it depends on how big your circle is in that universe, right? So 25 divided by 6, this is going to be 4 point something, right? 6 goes into 24 4 times, and then it's going to be 1 left over, and then 1/6 is a ratio of 16. So that's 4.16. Imagine the ratio of the circumference of a circle to a diameter is greater than pi. Students in geometry class would go crazy about that. Wait a minute, they would say, you're teaching us that circumference over diameter is 3.14. That is only in a flat space. If the flat space is like this and the straight line, geodesic is a straight line, then you're going to have always, no matter how big the circle is, the ratio of the circumference to the diameter is going to be 3.14 in that universe. In this universe, not really. It's always going to be larger than 3.14, and it could be really larger depending on how big your circle is. So in our case, it was way, way larger than 3.14. So on March 14th of every year, we actually celebrate Pi Day. And we say, oh, Pi is March 14th. Well, in this universe, for that circle, we would have to celebrate April 16 and call that Pi Day on April 16. So that would be a weird universe, right? So you can see here with this demo, the 3 different properties of the negatively curved space. The angles of a triangle add up less than 180. The ratio of the circumference to the diameter is larger than pi. And then also the straight lines diverge outward like this, right? Okay, thank you very much.